And so welcome to our June 30th, 2021 live lecture. We'll just start off the discussion today just looking at the calendar a little bit. Again, we do have the homework for the bending and transverse shear chapters 6, 7, and 11. That is due on Saturday this week. And then the exam due next Tuesday. Kind of where we're at in the course content is we're looking at the deflections of beams and shafts, and we will be able to finish that chapter 12 today. So we'll get homework ready for the following Saturday. But that leaves Friday kind of open for us. I think what would work out best is just to have a help session on Friday where I could answer any questions that you might have. And so send those in by email, or if you're joining in live, you can ask those on Friday. And so that'll be kind of nice for the 4th of July holiday weekend, not having new material being presented on Friday. It'll just be a Q&A session. And then I did find out that Monday is in fact a holiday. So we won't have class on Monday, July 5th, which will still work out well with our scheduling. When we get back together next week on Wednesday, we'll get into failure theories and combined loading. And we really only need a couple class periods to do that. So we'll be looking good finishing out the semester here at the end of July timeframe. And so that's kind of the scope of things. I guess, are there any questions at all?
No, I don't have any questions.
Okay, and then the good news is I did get through and graded the torsion homework yesterday and posted those solutions to D2L, so those are out there as well. And so let's go ahead and get started then on the chapter 12 lecture today. And so we kind of looked at the basic types of analysis for beam deflections on Monday. We looked at what happens if there's a distributed load, integrating back 4 times, solving 4 constants of integration. And then we looked at the basic cantilevered beam with a point load and finding that internal moment is a function of X and integrating back twice. And solving the constants of integration. And so today what we're going to focus on more is then another derivation based on the fundamental equations and integrating back to solve for the elastic curve. But we'll introduce continuity, the need to establish the proper displacements and slopes at points where you have another loading or boundary condition. And so we'll show how to do that. And then we'll get into the discussion on making use of the tables to then more quickly solve those problems. If you don't have to go through the integration, if that's already been done for you, you can turn an hour problem into a 10-minute problem. And so we'll discuss that. But first thing we'll do is look at, this is an older problem out of a textbook, I think the Hibbler textbook, but it's just a simply supported beam with constant E of I, E and I, and then the applied moment. So there's a clockwise moment M0 and a counterclockwise moment M0. A third of the distance from each end of the beam. And so the total length of the beam is 3A. And so what we want to find is the maximum deflection along the length of the beam and the slope at A. Sorry about that. And so solving for theta of A. And so for the analysis then, we really do want to draw a free body diagram showing our moments that are applied. And we have a pin connection and a roller, so those can only support a vertical load. And so we have A of Y and B of Y there as well. One thing we can see from this is that it is symmetric. And so we really don't need to do 3 cuts along the beam. We'll know that it's symmetric about the center. But then to continue on, we really need to know what the internal moment is as a function of X for this first section. And then we also need to figure out what the moment of X is as a function of X for the second section. And so we really have our 2 cuts that are then needed to draw then those free body diagrams and to look at those internal shear and moment as a function of X. And so just starting off then, if we sum our moments about A, what we'll find is that By times 3A plus an M0 minus an M0 is equal to 0. And so these moments are already canceling one another out. And that tells you that By has to be equal to 0. And since By is equal to 0, if you sum forces in the Y direction, it tells you A of Y is equal to 0. And so this is a good example problem just to understand sometimes things are just going to be 0, and looking still at then the free body diagram based on that situation. And so as we continue down, we'll look then at section 1.1. And for the first section, it's kind of interesting because we have then that first part, we'd have an A of Y, but that's equal to 0. And so all you are left with is your internal shear and internal moment. And if you wanted to clarify, you could always put a V1 and M1 here to designate that as the first section, but I just have it all contained here under the first section. But if you sum forces in the Y, you just end up with a minus V is equal to 0, which tells you that your internal shear force is 0 along that entire first section. And same thing with summation of moments of the cut. All you have is the internal moment, nothing else, since there's no A of Y. And so it tells you that your internal moment is 0. And so that's why I'm kind of saying this is kind of good to go through an example like this, so we can see that integration back through when things are equal to 0. And so again, this is one of those problems where you want to start out at that level of knowing the moment is equal to 0 and integrating back twice to figure out what your constants of integration are. And so again, M is equal to EI times d squared V dx squared. And we know that's equal to 0. So that's our first equation. When we integrate back once, we'll end up with a constant of integration on that right-hand side. So we have EI dV dx is equal to C1. Integrate back again, EIV is equal to C1x plus C2. And so even though our moment was equal to 0, as we integrate back, we still end up with our constants of integration. And we still need to apply our boundary conditions. And so V of 0, the displacement at that pin connection is 0. And so into that third equation, then if the displacement's 0 and X is equal to 0, that forces C2 equal to 0. But then for solving the slope, we really don't have any constraints here on this left-hand side that we can look at in terms of that second equation. It's a pin connection, so it can have a slope at that point, but we wouldn't know what that is. And so then we have to move on to the next section and look at that free body diagram. The one thing that we do know as we continue on is that the displacement at this theta of a distance x equal to a, for continuity to be satisfied, that displacement would have to be the same on the left and the right hand side of this point. And then same thing for the slope. The slope would have to be the same on the left and the right hand side of that point, just an infinitesimal distance. And so as we continue on, what we'll find is that we will have a number of equations then, and then we can set those equal to one another to solve for our C1 value. So that's the path we're taking. And so next section then, again, we start all the way over on the left-hand side where the pin connection is, because we want to keep that X definition and the datum remaining the same. And so we're now just cutting through that second section, 2, and so we'd have an internal shear and an internal moment. And this would be valid from X from A to 2A. And so for summing forces in the Y, we'd have a minus V is equal to 0. So we find again our internal shears equal to 0 in that section. And since it's symmetric, that internal shear is 0 throughout the entire length of the beam. So there is no transverse shear in this beam with the 2 moments applied. When we sum the moments about the cut, we end up with a doing counterclockwise the internal moment that we're looking for, and also then minus the M0 that's applied at X equal to A, and that's equal to 0. Again, remember, for these types of problems, it is kind of nice to sum moments about the cut, because then you don't have to worry about including that internal shear force in there either. For this problem, it's 0, but for other problems, it's nice to sum moments about the cut to not have to deal with that internal shear. There's no moment arm there. But now we know that the internal moment throughout that second section is just equal to M0. And we can set up our next 3 equations. M is equal to EI d squared V dx squared is equal to M0, our moment throughout that second section. And so when we integrate back twice this time, we'll end up with the EI dV dx is equal to M0x plus C3. And integrating back again, we have EI V is equal to M0x squared over 2 plus C3x plus C4. And so just looking at continuity and just the symmetry of the beam, the main thing is when you have a symmetric condition like this, the slope couldn't go to any positive or negative value here at the center of the beam, as that would provide for kind of a discontinuity if it's sloping up to the same point. And so what you know when there's something symmetric like this is that the slope at that center point has to be equal to 0. And so that's 1.5 times A, or 3A over 2 for that X location. And so that's the first continuity condition, just to satisfy the beam not becoming disconnected type of deal, or having an awkward transition of slope. And so what we find from equation 5 then is that the theta at 3A over 2 has to be equal to 0. So the slope at the middle of the beam is equal to 0. And so if we plug that into 5, we know slope is equal to 0, so everything on the left-hand side is 0. And then we have M0 times 3A over 2 plus C3. And so that was a nice continuity condition to place into equation 5, because it gives us one equation, one unknown. where we can solve for C3. And so C3 then is equal to just a minus 3 M0 A over 2. And we still have two constants of integration to solve, C4 here, and then C1 on the previous page. And so that's where more continuity conditions come into play. If we look at equation 2 on the previous page, we know that the slope there at x equal to a has to be equal to the slope at x equal to a for equation 5. For continuity to be satisfied at that location, x equal to a. And so that's the main statement there. Equation 2 is equal to 5 at x equal to a. And so theta a for section 1,1 is equal to theta of a of section 2,2. And when we look at that, again, theta is just dv dx, and we know that's equal to C1 over EI. And so the left-hand side is just C1 over EI. And then equation 5, plugging in x equal to a. Also, we solved C3 already as a minus 3 M0 A over 2. And so at this point, that slope theta of 2,2 is going to be equal to 1 over EI times M0 times A minus the 3 M0 A over 2. And so again, setting the slopes equal to one another at that point, x equal to a, allows us to have one equation and one unknown. The EIs will cancel. They're on both sides in the denominator, so they'll cancel with one another. And we can just simplify to solve for C1. That'd be M0A minus 3 M0 over A. This is the same as 2 over 2. So 2 minus 3 will give us a negative half. And so we have a minus M0A over 2 for our C1 term. And so now we've really established then that need for continuity, because we really didn't have any conditions on that left-hand side to be able to solve for C1. But when we look then at the second section, and we need to set those slopes equal to one another at that point of x equal to a, where they have to be equal to one another, we're able to solve then for those constants of integration. The other thing that has to be true at x equal to a is the displacements have to be equal to one another. And so again, equation 3 is going to be equal to equation 6 at x equal to a. And so the displacement for the 1, 1, and we're coming all the way back up here to equation 3, EIV equals C1 times x plus C2. Remember C2 0, C1 we just solve for. And we're solving for that displacement and plugging in our C1 constant and x value equal to a in that term. And so that ends up being a minus M0 A squared over 2 EI when you make that substitution in. And then for equation 6, that's going to be a 1 over EI times M0 A squared over 2 minus a 3 M0 A squared over 2 plus C4. And that again is just solving for V in equation 6, dividing through everything by EI, plugging in x equal to a in both terms, and then plugging in C3 is minus 3 M0 A over 2. One thing to be careful about with that is just remember you're plugging everything in. So there's an A term already in C3, and we're multiplying when x is equal to a. So we end up with that A squared term. And so always make sure you're looking at those products of the variable. And so we see that there with the a squared term. And so once again, what that does for us is it gives us one equation and one unknown C4. The EIs will cancel, and then it's just algebra after that point. We're subtracting off the, I guess I'm starting out with this one, moving it to the other side. So 3m0 a squared over 2 minus an m0 a squared over 2 minus another m0 a squared over 2. And so that ends up then being 1/2 m0 a squared for C4. And then that then uniquely defines the general equations. We've been able to go through and solve all of our constants of integration. We have our C1 term, C2 0, and then we've solved for both C3 and C4. And so then it's just a matter of plugging those back in to evaluate the elastic curves. And so that displacement over that first section is just a minus m0 ax over 2ei. And then theta of a is equal to a minus m0a over 2ei when you plug that back in for dv dx. And so one of the questions you're asked is what is the slope at a? And the slope is a constant from that left pin support all the way to the location of that first moment at x equal to a. So that's a constant, but the displacement is changing. And so that's kind of interesting to see that even though we had a 0 shear and a 0 moment through that section, we still end up with displacements occurring and that slope due to the boundary conditions and the loading throughout the beam. And then for that second section, as you plug back in the constants of integration, you just end up with the displacement is equal to m0x squared over 2 minus 3m0ax over 2 plus an m0a squared over 2 divided by 3 by e of I, that whole quantity. We could also figure out what the maximum displacement is. Just the way that is orientated, that would occur at 3a over 2 due to the symmetry. And so we're just plugging in a over 2 in for this, or 3a over 2 in for this. So the 3 gets squared and becomes a 9. The 2 gets squared and becomes a 4 times 2 gives us an 8 in the denominator. And then we have 3a over 2 coming in for x. So we end up with 3 times 3, 9 again, m0 a squared. Because remember 3a, a times a gives us a squared. Divided by 2 times 2 gives you the 4 plus an m0 a squared over 2. And 8 is a common denominator, so we're looking at 9 minus 18 plus 4. Will give us a minus 5/8 m0 a squared over ei. And so those are the types of things that might be important to solve. Usually that's where you have your constraints is on your maximum deflection and needing to keep that under a certain value. And so we kind of derive this out in terms of the x equal to a aspect. Oftentimes the tables are set up based on the length of the beam. And so we can modify this one to represent that as the length of the beam. And so as a function of L, the length of the beam, we know that A is just L over 3. And so we could put L over 3 in for A. And then that goes in the denominator. So 3 squared is 9. 9 times 8 is 72. So V max is just minus 5 M0 L squared over 72 EI. If you're looking at it from the length of the beam perspective as opposed to a third of the length as we've done. Let's see. Jordan, do you have any questions over that derivation where we did everything ourselves in terms of integrating, solving our constants of integration?
No, that was pretty followable, pretty lengthy.
Yes, yep, they do get long. Anytime you have continuity for each section of the beam, you have to draw your free body diagram and figure out your internal moment as a function of X. Integrate through, you'll have 3 more equations. So anytime you have like a boundary or a load that's applied throughout the beam, it's just going to multiply your number of equations by 3. And there's not really any easy way to do that. If you're really having to start from the scratch and draw your free body diagrams and go through, it just takes time to do all that integrating back and all the algebra to solve for your constants of integration. The other thing is you really want to do the algebra to simplify it down to the nice forms. Because if you're trying to just not simplify things, that's going to make things even more complicated. So always try to simplify things as you're going along. That'll make life easier. So next up, we will bring another table up. And so I've mentioned before, if you have tables that you can use to solve this out based on what's provided in the table, it can turn your 1 hour problem into a 10-minute problem. And so I thought I'd show you an example of how to do that for this particular case. And when you get into machine design, you'll be using Shigley's textbook. And they have a whole host of other common loading applications for their tables. And I'm going to go back just a little bit. We had looked at cantilevered beam with a distributed load yesterday or on Monday, and just giving the layout of how Shigley's notation is set up. One, they will tell you what their reaction forces are as a function of the distributed load and the geometry, the length of the beam, as well as the reaction moment. So those are a couple values that you did not get directly from Hibbler's tables in the back of the book. They also give you what is the internal shear and moment as a function of X. And then the Y that they're referring to in these equations is corresponding to that vertical displacement, where your Hibbler book uses a lowercase v to define the displacement in the vertical direction. Shigley's notation, they're just using Y for that. So just make a note of that. Y is referring to displacement, and they also give you what the maximum displacement is. So that's one nice thing about the Shigley tables, is that they provide you with more information. And so this is something I always provided as a handout in the ME 316 class. And when the faculty were using Norton's machine design textbook, that would come up students would ask me, hey, do you have that Shigley handout? That would be pretty handy. And so you have an electronic copy of this now, so maybe save a copy of it. Definitely will save you time in the future when you're doing beam analysis. But for this, you really just need to go through and find the boundary type condition and the loading condition that would match what we're dealing with. And it doesn't have to match perfectly. It just has to match in terms of the type of loading. And so we finally get down to the 8th example, and we see a simply supported beam with a moment applied some distance A along the length of the beam. And so this is giving us the fundamental relation that we need to solve for these parameters. And what we can do is see if we can get that same maximum deflection out of the table in terms of setting up the variables this way. And so basing this off of Shigley's table 8 here, first we have to redefine what A and B is based on our table and based on the loading that's provided. And so for relating it back to our problem at hand, we have to realize that main thing is this is a counterclockwise moment that's being placed on the beam. And so that would correspond to our second moment over here on the right-hand side. And so with that, it would really correspond to this one. That moment is going to cause the, say, the center point to deflect down a certain distance. And the other moment on the left is just going to cause that to displace down that equal magnitude. So all we have to do is, with the one moment here on the right, analyzing the maximum, analyzing the displacement at the center, and then multiplying that by 2 will get us the same result as what we did going through the long methodology. And so that's our goal. It's the one on the right-hand side. And so for this definition, A would be equal to 2L over 3. It would be the one over the on the right-hand side. And then B would be the remaining L over 3. And so this is based off the definitions in the table. One thing I'm not a big fan of is the lowercase l that Shigley uses. So I'm using the uppercase L again in the lecture notes here. And then y of AB is equal to that displacement V of AB from Hibbeler's definition. And so it would be our M, they say MB, we have a M0 that's applied. So it's M0 times X over 6EIL times the quantity X squared plus 3A. A is 2L over 3 quantity squared minus 6A 2L over 3 times L plus a 2L squared. And so that gives us our displacement as a function of X for that first part of the beam from 0 to A, all the way over to 2/3 the length of the beam. We want that portion of it so that we can solve what is the displacement at X equal to L over 2. That'll be then the displacement caused by that 1 and 0. So V max then is just equal to 2 times that displacement that we would get out of this at L over 2, because we have the second moment applied as well. That's just going to double that. And so just doubled it with superposition there. And so we're looking at V max then, multiplying that by 2. So we have 2 M0L and Okay, X is equal to L over 2, and so that's why we get the 12 in the bottom here. So we have 2 M0, L over 2 will give us a 12 in the denominator times EIL, also in the denominator, and then we're plugging in L over 2 in for the X term. So we get an L squared over 4 plus 4L squared over 3. This will become 9. We'll cancel the 3 to leave us 3 in the denominator, and the 2 squared will give us 4, minus 12L squared over 3 plus 2L squared. And so a common denominator on all of this is 12. So that'd give us a 3L squared over 12 plus 16L squared over 12 minus a 48L squared over 12 plus a 24L squared over 12. And we can simplify then as a minus 5L squared over 12. And then when we multiply those two through, we get the maximum displacement is equal to a minus 5 M0 L squared over 72 EI, which matches what we got before when we did it the long method of integrating back through. Let's see. The other thing that you realize from this is we were able to get the full elastic curve. And so based on just using the tables alone, that really provided the method or all that was needed to get the full displacement as a function of X for the left-hand side. If just one moment were applied. And so you would have to take that forward from that point and take into account the second moment being applied so that you could finish out that displacement as a function of X for that left-hand side. And so we're not quite there yet with the full equation for the elastic curve because we're not taking account into the other side. But if all you're wanting to do was to solve for the displacement at the center of the beam, this is all you needed was that much information. Using superposition, you can back it down to that point. I believe that was kind of the purpose, was solving that maximum deflection and then the slope. But that gives you the background there on making use of the tables for that purpose. And then solving for the slope, you really would have to get in that other moment term in there and then take the derivative with respect to X to be able to solve for the slope. All right, so we're getting through there a ways. Let me see. I think this one will be quick. Yeah, we'll do this one and then we'll take a break. I'm going to open up the handout from Monday. I think I can do this with Hibbler's. Because you really should feel comfortable making use of any of the tables, whether it be Hibbler's tables or Shigley's tables. And so this next example problem will again just be an example in making use of the tables to solve problems so that we don't have to go through that full integration process. And so we'll see what we have here. Remember the assumptions again, small deflections. You're probably going to establish most of that on design codes on what is allowed there for deflections. E and I are assumed to be constant along the length of the beam, and it also is neglecting the transverse shear effects. And so all the displacements and slopes we've been calculating is not taking the transverse shear contribution into account. And we might touch on that a little bit, looking at the Castigliano's method. But those effects are generally negligible. And so when we're dealing with problems that have multiple loadings on them, really it's just a matter then of using that principle of superposition and summing those contributions together. So this example problem, 1221, we're given that we have a 3 meter long beam. It's circular with a 100 millimeter diameter, and there's two 6 kilonewton meter moments applied and an 8 kilonewton force applied. And it is a simply supported beam. I think that's one thing I kind of missed. Pin was center point load, which would be a simply supported. The steel shaft has a Young's modulus of 200 gigapascals, and again, the diameter of the shaft is 100 millimeters. So we finally have an example problem with numbers, so we can figure out the actual magnitude of deflection and just not work it down into an algebraic relationship. Those algebraic relationships are nice because then for any beam that has that type of loading, all you have to do is plug in the values and you have your displacement. So we'll do the similar thing here, is we'll solve it algebraically and then plug our values in when we're done. And so looking at that, it looks like I focused on the 8 kilonewton force first. That shows up on the top of your Hibbeler tables. Looking at V max there is equal to a minus PL cubed over 48 EI. And so we know that displacement is going to occur due to the 8 kilonewton force. And then we have moment on that same page of the PowerPoint. We have a moment that's applied on the right hand side of the beam, which represents this one. And so we want to know what the displacement is at the center of the beam. And so for this problem too, everything is symmetric, so that forces the maximum displacement to occur at the center of the beam. And so we have the one moment M0 on the right hand side. We can solve for the corresponding deflection at x equal to L over 2. And then when combining those, we just need to double that because we have another moment on the left hand side. And so first step is just solving the displacement at x equal to L over 2 based on the 6 kilonewton meter moment on the right. And this one we have to be careful when we look at the table, because they do give us a V max based on the one moment, but that occurs at x equal to 0.5774 L, so not at the center of the beam. So what we want to know the displacement at the center of the beam, so we have to use the elastic curve that's given here and solve for that directly. And so we have a minus M0 x over 6 EIL. times L squared minus X squared. And all we're doing is substituting L over 2 in for X. When we do that, the L's will cancel here outside and give us a 12 in the denominator. So minus M0 12 EI times an L squared minus an L squared to the 4th. And that is the same as 4 over 4 minus 1 over 4. So it gives us 3/4 L squared. And when we plug that back in, we'll end up with 3 canceling the 12 to give us 4 times another 4 give us 16. So we have a minus M0 L squared over 16 EI based on one of those moments being applied. And so the superposition then is the maximum displacement is that displacement that's caused by the 8 kilonewton force plus 2 times the displacement caused by that 6 kilonewton meter moment. Again, the 2 comes from the effect of the moment on the left-hand side would produce that same displacement as the moment on the right-hand side. And so the displacement of the, due to the 8 kilonewton force was minus PL cubed over 48 EI. And the displacement due to the moment is then plus 2 times the negative M0 L squared over 16 EI. And now it's just a matter of plugging in variables, the numbers to that to be able to solve. I solved I out because it goes into both of them. Pi d to the 4th over 64, d being 100 millimeters, will give us an I value of 4.908 times 10 to the 6 millimeters to the 4th. And they gave us a force of kilonewtons and a moment of kilonewton meters. And so I decided to use units of kilonewton millimeters, which will give us the Young's modulus needing to be entered in terms of gigapascals. And so when we do that, the load P is 8 kilonewtons. The length of the beam is 3 meters. So that's 3,000 millimeters. E was 200 gigapascals, and I we just solved for. The moment was 6 kilonewton meters, and so that's 6,000 kilonewton millimeters. Length of the beam again, E again, and I again. And we already took into account the 2 there, canceled with the 16 to leave us 8 in the denominator. So that's already in there. But that's then all of the values that's going in. And we get then a minus 4.584 millimeters based on the application of the point load in the center. And then we get minus 6.875 millimeters due to the application of both of those moments. So each moment would provide half of this displacement. So combined, it's double that. And then just subtracting those, we end up with maximum displacement equal to 11.5 millimeters. And the negative just indicates it's going to displace downward. And so for this problem, we kind of saw the benefit of what we wanted to know was the maximum deflection. And we were able to just based on the either the maximum deflection, if that's what we're after, we could use that directly, or if we needed to substitute L over 2 into the elastic curve, we could just make use of both of those expressions and not have to go through the whole integration process to solve for that. We're just able to solve for that directly with the principle of superposition. And so that is a good place to stop. I guess, Jordan, do you have any questions over that example problem?
No, that was pretty straightforward. I like that a lot better than deriving all of that myself.
Isn't that nice being able to make use of tables and not have to integrate and solve concepts of integration?
Yes, I enjoy not having to reinvent the wheel
Yeah,
every
and
homework.
I think it's important that students are capable of doing that integration if needed. But if tables are available, it makes way more sense from an engineering standpoint to use the tables. Just the effectiveness of time, essentially. And so I kind of like that balance. From what I'll do for, say, the second exam is having a balance between you deriving something and then also making use of tables for other problems. So yeah, I think we're good there. We do have one more example problem, so I think it would be good to have a 5-minute break, and then we'll meet back up to do the last example problem, but we should be able to finish up a little bit early today.
Okay.
All right, we'll see you in a few.